Hello IB, this is the start of chapter 5 which looks at functions again. We've spent the first part of the year so far looking at a whole range of functions, and this chapter pulls those together, extends on different sorts of functions, as well as consolidates all the transformations that we've already been talking about. So at the moment when we talk about a family of functions, we've talked about, in this case, a linear function, and we've got a whole lot of the others below. In any function we're talking about the term variables. So when I'm just trying to get a bit of pen action here. All right, so when we're talking about variables, we're talking about, in most cases, the x and y, or later when we're looking at movement, motion, we'll be looking at like distance and time. So they're the two key variables that are being analysed. Sometimes we'll have other letters appearing in our equation and we use the term parameters. So when we talk about y equals mx plus b, our y and x are our variables, but our m and b determine things about the function, but they're not our key variables. So they affect our equation without being the variables. So far, the functions that we've looked at are linear, quadratic, cubic, exponential, logarithmic, and then the reciprocal ones. So they should all look familiar to you. The notation should be familiar, and in this case, they've given some restrictions for the parameters a. Obviously, if a is equal to 0, then you don't have a linear function or quadratic. And we've also put in here that domain restriction, because you can't take the log of a negative number. And again, with the reciprocal one, we can't take the fraction where x is equal to 0 in the denominator. What we've also done when we've looked at our graphing, so when we've looked at, I'm just going to shift this out of, oh no, can I move it? Yes. So when we're considering our calculators, we want to look at the different features. We've talked about axis-intercepts, x-intercepts, where y is equal to 0, the y-intercept where x is equal to 0. We've talked about gradient, and that's basically relevant for linear functions only, but we will be going into gradient more of a function, but not until we hit calculus next year. We've talked about the turning points, the maxima and minima. We've also talked about domain and range. And all of these terms, this should be all now very familiar to you. We've talked about values for x where the function doesn't exist, and that would affect our domain, obviously. So we can't have x equal to 0 in the denominator. That's our first scenario. In a square root, we're not going to be taking square roots of negative numbers. We're not going to go into complex numbers in the standard course. And in our logs, we're not going to be taking, the argument can't be negative or 0, so our argument always has to be greater than 0. We've talked a lot about asymptotes. If we want our vertical asymptote, that's where your function doesn't exist. That's all those conditions we mentioned up here. For a horizontal asymptote, then we want to see what happens to the function as x approaches our plus or minus infinity. So as x goes out to plus or minus infinity, what happens to our function? We can either look at that in a graph to see what happens, check on a table of values. You might be able to work it out algebraically as well. Another part we've talked about are end properties as x approaches plus or minus infinity. So we want to think about, does our function go up at the end or does it go down at the end? Which way is it moving? So they're all key things that we'll look at. So during this topic, we're going to be looking at a couple of investigations. So the next lesson we'll look at an investigation that goes through a whole lot of different functions. And we're going to look at polynomial functions, and eventually we want to be able to come out with a summary so that you're very familiar with anything from a linear, quadratic, cubic, up to quartic, and then even higher powers, that you're familiar about how to get the number of turning points and what they might look like. Another part of this topic is where what we call wacky functions. Sometimes you're going to be given a function that you've got no idea what it's going to look like. This will obviously occur in your paper 2, where you have a calculator. So in this example here, we've got this graph, this function here, y equals 2 to the x divided by x minus 2. And we've set a domain restriction here of -2 up to 4. And so you'd be asked to say, put this in your calculator and then determine all these features of the graph. And then at the end, you need to sketch it showing those features. So pause the video now, put this into your calculator, and you'll hopefully come up with that graph, and have a go at filling in the axes intercepts, the turning points for the function, what are the coordinates, equations for any asymptotes, domain and range, and then look at how you'd go about graphing it. So pause the video now and then come back to that. All right, so hopefully you've had a turn at that. With our axes intercepts, we can see that there's no y-intercept here, that there's an asymptote there, but we do have an x-intercept here at 1 and at 2. So our x-intercepts are at 1 and 2. All right. Let me just write that again. All right, so intercepts at 1 and 2. To find our turning points, you're going to be looking for a minimum value down here. So you'll need to do that on your calculator, and I'll find that value. All right, so with the asymptote, this function, the easy one is this x equal to 0, because we see in the denominator here that can't be 0, so that gives us the vertical asymptote at x equal to 0. That's that one. The other one here is at y equals -2. So even though this part of the function dips down, there's an asymptote that comes across here at -2. So at y equal to -2, we have another horizontal asymptote. So in terms of domain and range, we need to take into account these asymptotes. So for our domain, we're going to have x doesn't equal 0, otherwise all x values are fair go. For the range, we now see we get a minimum at this point that we've identified, and it's going to be above -2. So our range is a little bit different to what we've normally seen. So our y is going to be less than or equal to the y coordinate of our minimum, of our turning point. So -0.116, and it's greater than -2. So it's not going to equal -2. That's because this is an asymptote, but it can equal -0.116. No, correction. Pause. We've got to actually, that's where it doesn't exist, so we need to do it the opposite. Sorry about that. Okay, got that fixed up. So our range is less than -2. It can't equal -2 because that's the asymptote, and it's greater than -0.116. So that's our range. When you come to sketch that function, then you make sure you show all those key points on here. For a given domain, if they state this is our domain here, then make sure you stop your graph with a point and don't keep going onwards there, and stop it at a point here. Don't put an arrow. If that domain restriction doesn't exist, then you can put arrows on the end. It's okay putting arrows here because that's within the domain that they're going to those y values. So just watch that with your graphing. It's very important you look at your domain. The next thing I want to look at was this part here where we've got two functions and you're trying to solve these and finding different values for where they're true. So here we're graphing the function of y equal to 1 on x, which is this one I've done in blue, and we've got y equal to 2 minus x, and that's going to be a straight line, so I'll just put that in as a straight line. Go green, and that's a straight line, and it touches, and it can be a double-ended arrow. Okay, so I've drawn that in, and when we sketch that in, you find that this line has a slope of -1, intercept at 2, and we're going to find it touches at 1 point. So when it asks you then in part B to find any solutions, we're looking for the points of intersection, and you can either do it graphically and solve that and find there is that one point of intersection. Otherwise, we can do it algebraically. Do you remember how to solve this algebraically? Hopefully you look at that and go, oh, if I multiply everything by x, then I end up with a quadratic. So I end up with 2x minus x squared equals 1. Pause your video and have a go at completing that. So when we solve that, you come out with x equal to 1. Substituting it back into one of your equations, we come out with the y coordinate 1, so it intersects at 1, 1. So our solution to this equation is x equal to 1. They're not after the coordinates. That's what you'd see when you're graphing it. The next part then says, for this domain, for what values of k does this have one solution, no solutions, or two solutions? At the moment as that stands, it's like, well, how am I going to solve that? This is A and B here together. So if I have x plus 1 equal to k, then I can just simply rearrange that to make it match what we had started with earlier. So always assume that these questions have some sort of connection to them. So this is the same as going 1 over x equals minus x plus k. All right, so basically we've got our linear equation here, and in this case, this is our y-intercept. So it's another line that's parallel to this one, and let's give it a y-intercept of 0. That would just be where k is equal to 0, and we've got y equal to minus x. So in other words, it's saying, how can I shift this line around, changing the y-intercepts, so that I can either have one solution, no solutions, or two solutions? So if we look at our graph here, when it intersected there, we have one solution. And if we had another line down here where it cuts through here to get one solution, then what would be the k value here that gives us one solution? So if that was at plus 2, this is going to be at minus 2. So we're going to have k equal to, what do we have here? 2 or minus 2. All right. If I want no solutions, that's like the red line, then that means our y-intercepts have to be somewhere between these two. So anywhere I shift this line, if I shift this up here or down here, we don't get an intersection. Don't get an intersection. So there we are. So our k values in this case have to be between those two. So if I have k that's less than 2 or greater than minus 2, then I get no solutions. There's no intersection between my line and the hyperbolic function. If I want two solutions, that means the line here, I'm just going to trace over it to translate it. If I shift that up, I now get two solutions, say here and here. So our k value obviously has to be, which is our y-intercept, has to be greater than 2, or k is less than minus 2. All right, so again, that's a different way of looking at functions that you can't just solve on your calculator with the k value. So hopefully this will give you some ideas, and then we'll look at this further in class. Thanks for listening and have a great day. Bye for now.